Hey, this is a video for Lesson 4 for AI and Game Technology at Utrecht University. Today we cover learning from data. Note that this lecture, the videos I split in two because we cover two different topics. So learning from data, and we have given data and we want to train a neural network. So this is a classic supervised learning task. Here we will not deal with how did we get the label, the data. We just assume we have the data together with the labels. And in supervised learning, we train on it, and then the computer tries to predict, given some new data, what the label should be. So the data that you get from games will be like the sequence of gameplays. And you have to do a little bit of pre-processing here. So first thing you do is maybe a data point would be a single board state, for instance, the empty board or some move at some location. And then the label could be, for instance, what would be the turn that the agent does next, or the player does next. We don't know whether it comes from human or from computer. Or you could say, okay, so we know this board state, and I know who won this game, and that could help you predict who good this board state is, and it could give you an approximation of the value according to the agents or the policy that was used. Okay, so assignment 1. Okay, so in a neural network, we need input and output vectors. So we need vectors, that's here the emphasis, and so just translate those for data points to actually input and output vectors. Note here, in the first two examples, we say who the winner is. In the fourth example, we say what would be the next turn, let's say, of white. Second question, so there are different ways that you could translate those things into a vector. Try to describe at least two different possibilities, and maybe think about what would be the pros and cons. And then now imagine you have trained a neural network with these two different ways, these two different types of labels. How could you use this in order to have an agent? Just think about some very simple ideas. And again, post your answers on MS Teams. Okay, the problems that could come up with is that your data is not good, right? It may be inconsistent, and it may be just that your agents are very bad, and then you can't really expect that your neural network will be really great either. So here, for instance, if you let two random agents play against each other, then maybe you don't really want to copy their behavior. Okay, so maybe you want to have a good agent, and then comes problem 2, which is that in your data you may have unseen states. So imagine this racetrack, and imagine we know all these data from Formula 1, racers who are like really, really good at racing, and they would always race the ideal route or very close to it. And then you train neural network on it, and then you let the neural network run it, but would just do some subtle mistakes and slightly deviate from it. And when it's deviate, it will deviate more because it goes into this territory on which it's not really trained. And since it's not trained, its behavior, it's something that the neural network has never seen. Its behavior will be somewhat erratic and then will lead to a crash. So so you want your data to be diverse and cover lots of different states so that your neural network can generalize. Okay, so these are basically the three qualities you want to have from your data. You want to have a lot of it. You want to have a good quality, so the turns that you do or the value that you get, they should be close to the truth of the true value if you play optimally. And you want to have a diversity, so again, you don't want to just see a lot of the same states, but you want to see a lot of different states. Okay, let's think about assignment 2. Okay, so we have these different types of agents that we described in the lecture so far. So there's a random agent, the agent based on the armed bandit problem for your homework assignment 1. Then we had the score agent, and we can also think about an agent that comes from a neural network based on the assignment, the previous in-class assignment today. And then all I want you to do is I want you to rate these agents on the data you would get out of them according to these 3 measures. So the easy way to do it on your whiteboard, you can just make dots and then move these dots left and right as in the assignment of the previous class. Okay. And yeah, so when you get data, you often get it from some databases, and or you may have generated it yourself, but then you may not be able to directly train a value function. So think about some scenarios, at least one, but I think maybe even more than one, when you can't train directly a value function. Yes, just think about where this could appear. Again, write down your answer and post it on MS Teams. At last, I want to show you a more sophisticated way on how to use a trained network in order to help you with your multicolored research. So it could help to reduce branching. So let's say you have your game tree and it has, as you know, these 9 options, and maybe it could have even more. And these are too many options to branch through because you're not getting very deep into your tree. And then what you get out of it is not really very meaningful. You go into a lot of options just to explore them a few times. And that's annoying. But now imagine you have this trained neural network and it trains your probability function because it kind of tried to figure out what would be the next move. And then in this way, you get this probability function, which somehow says, oh, well, in this option, you go with 5%, maybe some other option you want to go with 20% of the cases. Now, you can use this in order to help your branching. And I want to tell you some 3 ways you could do this. I'm not saying these are the perfect ways, but it's just some possibilities you have. So when you branch, you could branch according to probability. This means, so remember in multicolored research, you have a phase which is called selection, and then you pick one of the children. And now you just pick the child according to the probability, or maybe with the highest probability. Let's say according to probability. I guess if you pick the highest probability, you would always pick the same, so you should do that. And this has one downside, which is it could be that you go into one child which has fairly low probability. But because of chance, you're unlucky. And what happens in this in this child is that the value it gives back is pretty high. So usually this is not a problem if you do multicolored research. You go into some child, you go into some branch, and if it has a high value, you go there more often, and then you may quickly figure out that this high value was a coincidence. And if you go a little bit further down the tree, you figure out actually very quickly this turns out to be something that's very bad for you. But now you would do this if you would just follow this first idea and do the selection according to probability. So you maybe go there only once, think it's great, and you never correct your estimates because you don't go there more often. So there are downsides of this idea. The second idea would be you could pick only the top 3 choices, right? So you have the probability function, and then you pick the top 3 choices. So this clearly reduces your branching, and those choices, and you can go much deeper into the tree. It's just that these probabilities, they may not be super reliable, and there are some options that are fairly good and that you would just never ever come to explore. And even if you have 10,000 explorations, you only figure out which of those three options is good, but your neural network may have missed something, and you cannot correct this anymore. So you could be here a little bit more sophisticated, that maybe you do this only, you don't do this for the top layer, but only afterwards. So a third option would be that, by the way, so what really the strength is of the second option is that it's very simple. You can do this and you don't have to think a lot about it, right? You just go ahead and do it. And it may give you something nice, and how well it works, well, you have to try it out. And then there is something maybe more a proper solution, but that may be much harder, which is you have this formula in your upper confidence bound that you use, but now you make a new formula, right? And so before you had this balance between the quality from the values that you get and the confidence that you need to balance. But now you may balance three things. You get some values from some score function or some value function that you backpropagate, and you get your probabilities from the neural network, which are also meaningful, and you have the confidence. And here you have to see, okay, if I branched in some option quite a lot, let's say I went there 100 times, I chose this child, then maybe the score function becomes very meaningful. But if I've been there only once or twice, the probability is maybe more meaningful. So you have to balance out those two things and see how to do it. So coming up with such a formula may be non-trivial. So that would be something you have to do on the theoretical side. But then there will be some factors, some constants that you have to fine-tune. There would be now two constants, not just one. And this fine-tuning may be more difficult than it is if you have just to fine-tune one constant, one parameter. So yeah, so I just wanted to show you that this neural network could help in many ways. Yeah, so that it's good to have, not just for maybe immediate selection, but also for planning, and even if you just get a probability function. Okay, that was it. Thank you.